back. We are continuing with our second chapter, and now we have arrived at one of the important topics of second chapter, that is capacitance and capacitors. From the word itself, the derivative root word itself tells you capacitor or capacitance gives us an idea about an ability to store, capacity, ability to store or capacity. Now we all know that whenever some charge is given to a conductor, its potential rises. Why? Because you know the potential is kq by r. From here you very clearly know that whenever you give some charge to the conductor, its potential increases. Some more charge is given, potential increases still further. Hence you can say that Q is directly proportional to V. And if I want to introduce a constant, I can say is equal to CV. What is this constant? Yes, this constant is now called capacitance. This constant is called capacitance. C is equal to Q upon V. This is the mathematical way of writing the constant C. As I told you, when you keep increasing the charge on a conductor, its potential increases and the ratio of Q by V remains constant. And if I take the units, it is coulombs upon volts, and this is nothing but your unit for capacitance, which is called farads. Now we are in a position to define capacitance. It is the measure of ability of a conductor to store charge. It is the ability of a conductor to store charge. And what is capacitance? It is the electrical capacitance of a conductor is defined as the charge required to raise its potential through 1 unit. This we got from here. Electrical capacitance of a conductor is defined as, C can be defined as, if I have Q is equal to 1, or let me write, if the potential, if V is equal to 1 unit, then C is equal to Q. The definition comes here. Electrical capacitance of a conductor is defined as the charge required to raise its potential. This is raising its potential through 1 unit. If the potential is 1 unit, then the charge required to raise the potential of a conductor by 1 unit is called electrical capacitance. Capacitance is very much a scalar quantity. Charge and potential, they both are scalar quantities. SI unit is farads. The other practical yet smaller units are microfarad, which is 10 to the power minus 6F, nanofarad, which is 10 to the power minus 9F, and picofarads, which is 10 to the power minus 12F. Now we will continue with types of capacitors and basic principle of capacitor. That what are the different types of capacitors we can have, how can we represent them pictorially, and what are the uses and all these things. First and foremost, a capacitor consists of 2 conductors. How many conductors? It consists of basically 2 conductors. Sometimes it can have only one single conductor and the other conductor can be supposed to be at infinity. That is a different situation. Otherwise, generally a capacitor consists of 2 conductors. The 2 conductors can be 2 plates, they can be 2 cylinders, or they can be 2 spheres. Or if you are having one single, earth is also considered to be a capacitor, and we consider that the other conductor is at infinite distance. So basically it has 2 conductors, they can be plates, cylinders or spheres, separated by non-conducting medium, such that, how are they separated? Basically they are separated by a non-conducting medium generally, and such that it can store, what is the purpose? It can store large amount of electrical charge in small space. Second important point, 2 conductors carry, the charge on them is equal. 2 conductors, they carry equal but opposite charge at any instant. Then how to represent them pictorially? If it is a fixed capacitor, fixed value, then it is represented by 2 parallel lines. And if it's a variable one whose value can be changed, it is represented with an arrow in between. Types. Now, based on criteria chosen is shapes. If you are dividing the capacitors based on the shapes, if the criteria is shapes, then the type can be parallel plate, spherical, cylindrical. These are the varieties. But if you categorize the capacitors based on the nature of dielectric medium between the two conductors, if that is the criteria, here I have written types by, if you divide by shapes, then these are the varieties. If you divide by dielectric medium between the plates, then they can be of types electrolytic, paper, mica, ceramic, and so on. Purpose. The purpose is to store charge and store electrical energy. It has the ability to store charge and release large amount of charge. Uses. Mostly it is used in computers, electronics, radio sets, TV sets, etc. etc. Now we will look into the basic principle of capacitors. Now we will see the basic principle of parallel plate capacitor. Just now I told you based on the shapes, capacitors can be of parallel, cylindrical or spherical types. But in this chapter, we will be concentrating only on parallel plate capacitor, because CBSE syllabus and NCERT talks about parallel plate capacitor. Of course, there are some numericals given in the exercise pertaining to cylindrical as well as spherical capacitors. Those formulas we will cover in the forthcoming episodes. Today we will be concentrating only on the parallel plate capacitor. The basic principle. Capacitance of a charged conductor. I can have a single charged conductor and its capacitance can be increased appreciably. How? By bringing another uncharged conductor. It should be a conductor, but it should be uncharged, it should be neutral, close to it. This is the basic principle. You have to learn it by heart because you may be asked to state the principle. Capacitance of a charged conductor. Let me demonstrate with an example. Step 1. I have a conductor, I call it by the name A. Can you see? I have a conductor plate A and I have another plate B. A is given altogether positive charge and in between A and B the medium is air, and the conductor B initially it is uncharged. Initially conductor B is uncharged. Step number 2. This is step number 1, this is step number 2. Initially the uncharged conductor is brought close to the charged conductor A. Now by bringing uncharged conductor we are trying to increase the capacitance of plate A. Step number 2. What happens? There is some induction of charges. This we have already studied methods of charging of conductors. Induction is a method where you can charge from certain distance. So due to the positive charge on the plate A, the electrons on the conductor B, they shift towards the inner side. This closer side to the plate A, the electrons come to this side and the absence of electrons is marked as positive charge on the outer side. Inner side is negatively charged, that means the electrons, they prefer to get closer to this plate A because it is positively charged, and the absence of electrons is marked as with positive charge. This is step 2. Now what happens? Because of this negative charge on plate B, the effect on plate A, the effect of charge A, effect is decreased. Try to understand, effect of positive charge on plate A decreases. When I say effect is decreased, I just want to give an example. Suppose you are moving in a car with your ACs on. Now you have kept your AC at a particular level, but still at times you may feel that it's not that effective. Why? Maybe some door or some window is open. So what? By opening a window, you are, without decreasing the level of AC, you are making it less effective. So without decreasing the charge on the conductor A, you are making the charge less effective by bringing negative charge close to A. Now charge on A has become less effective. If you want to increase the charge of it back to the original level, you can always give some more charge. Now it is welcoming more charge because the effect has been reduced. If you want to bring it back to the original potential, you can add some more charge. So now the ability of conductor A to accept more charge has increased. Now it is in a position to accept more charge. So the capacity of A to accept more charge has increased. Now step number 3, further what we have done, this positive charge, somehow it is contributing to the effect of positive charge. The outer positive charge is contributing to the effect of this positive charge on plate A. Now in step number 3, what we have done, we have connected the conductor B to earth. What happens? The moment we connect it to earth, the electrons come out of earth and they neutralize this positive charge. Means, suppose there is a shortage of 4 electrons, then 4 electrons will come from earth and neutralize this positive charge. So what happens? Now the conductor B is left with only negative charge, no positive charge to add or to enhance or to support the conductor A. It is left with only negative charge, this negative charge. And this negative charge is decreasing the effect of positive charge on the conductor A, hence decreasing the potential. Now in order to bring it back to the original potential, it can be given some more charge. Means what? Its charge accepting capacity has increased. It is now working as charge storing device. Now let us see the mathematical expression. Very important. This is important. Two conductors X and Y, I have given them names X and Y. Conductor X is given a positive charge Q and it has surface charge density plus sigma. Conductor Y is having negative charge minus Q. It is having negative surface charge density minus sigma. The electric field, the medium between them is there. The electric field is parallel and uniform. The electric field is here uniform. The electric field is uniform. And the value is sigma upon epsilon naught. This is something we have already seen. Now we want to calculate the capacitance of this parallel plate capacitor. So capacitance we have already seen, it is the ratio of Q by V, charge by potential. Now charge can be written as, I can write this, we know that Q is equal to sigma A. Because sigma is equal to charge per unit area. So Q can be written as sigma A upon V. We are doing this derivation. Now V can be written as, we know that electric field E is equal to dV by dr. Of course it has a negative sign which indicates the negative potential gradient, but here the field being uniform, you can write E is equal to V by d. So V becomes equal to ED. Substituting, C is equal to sigma A upon, in place of V I will write ED, and in place of sigma A upon, in place of E I can write sigma by epsilon naught. That I can write here. This can be written as sigma A upon, E can be written as sigma upon epsilon naught, that epsilon naught goes up into D. So epsilon naught gets cancelled. C is equal to epsilon naught A upon D. This is the final expression we are getting for capacitance. Hence, we conclude capacitance of a parallel plate capacitor depends on number 1, area, this is A, which is nothing but area of the plates, D, distance between the plates, this is the distance, and epsilon naught is absolute permittivity of free space. So this is the derivation, basic principle and understanding. We will continue with the forthcoming topics in the next